Welcome back, everybody. So we're going to be starting our unit on vectors, polar equations, and parametric equations. So to start, we're going to begin with vectors. So vectors are a fundamental mathematical object that is pretty popular in physics, obviously. So if any of you have taken physics, you've seen vectors before. And so when we think of vectors, we're going to be thinking of descriptions of physical phenomena. And we use vectors to kind of visualize, in particular, lots of different forces. So there's kind of two basic ideas that we want to discuss to start, which is scalars and vectors. And so when we look at all of these kind of terms up at the top, distance, displacement, velocity, acceleration, speed, etc., these are going to be descriptions of things that are either vectors or scalars. So the scalar quantity is simply going to be a number. So a scalar quantity for us is going to be something like speed. So if I say, I'm going 45 miles per hour, that is telling you the speed at which I'm moving. But what it doesn't really tell you is like where I'm going, right? So I'm moving with this particular speed, but in which direction am I going? So if we're measuring a vector quantity where speed is going to be a part of that calculation, what we would measure for the vector is what we call velocity. And that would be the speed I'm traveling at in a particular direction. So when we talk about velocity is going to be speed plus direction. And that might be at an angle of 30 degrees, that might be headed east. So direction is going to be something that we can define in lots of different ways as well. So when we think of a vector quantity, it's going to be described by a magnitude or length measurement and direction. So there's kind of two components to a vector quantity. And what that's going to mean in a lot of cases is that the scalar quantity itself is going to be maybe a measurement of some sort of vector. So in this case, if we're talking about speed and velocity, speed is going to be the length of the velocity vector. Okay. And we're going to kind of have to figure out what we mean by length. So there's going to be kind of a geometric interpretation that we focus on. But if we're looking at these other words here, we can kind of go through and try and figure out, well, who else is going to be a scalar among these? So we'll start with distance. So distance is going to be a scalar quantity, because I can travel 500 feet, but I don't necessarily know in which direction I'm traveling 500 feet. So the kind of corresponding vector to distance is going to be displacement, which can typically be thought of as the change between two different points in time, or the change in position at two different points in time. And so that is going to have a particular direction. So up or down, left or right. It's going to tell us in which way our particle moved or object moved. Acceleration is going to be another vector. So we can think of gravity as kind of the most common acceleration characteristic that we kind of discuss in most classes. But we're going to have some other things. So work is going to be a scalar quantity, and that's going to be the amount of energy required to move an object a certain distance. But again, the distance is not necessarily going to be part of the calculation for work. Force in general, so F equals ma might be an equation you've heard of before. So force is a vector, which is mass times acceleration. Momentum is a vector, that's mass times velocity. Energy, potential, kinetic energy, those sorts of things, those are scalar quantities, and mass is also a scalar quantity. And so for the equivalent vector form for mass is going to be weight. So the weight is going to have a particular direction because it's going to take into account the acceleration of gravity. So just to start, these are kind of our two basic ideas that we're going to be focusing on to start, which is the scalar representation of values geometrically, and then how the vector, involves scalars themselves. So let's get into how we're going to represent these vectors geometrically. And so we can think of these vectors as directed line segments. This is going to be kind of how we think of vectors for this chapter in particular. But note, vectors don't have to be simply these directed line segments. Vectors can have curvature to them and other things. But to start off, we're going to think of them as these directed line segments and that have direction, right? So there's going to be an arrow that we add in here, and we'll put an arrow in the notation that we use for these objects as well. And so the two key components, of course, are magnitude and direction. So we can see the magnitude is the length. So note, magnitude is just going to be the length of the vector. So the vector is not an infinite length line or ray. It's going to be a finite length value. And the direction is going to be represented by the measure of the angle from standard position wherever that vector is located. So both of those things are going to be key components. So if I'm drawing a vector, again, it's going to look like a ray with a starting point and then an ending point with an arrow at the end. So the tail is the starting point, the head is the ending point. Sometimes tail is called the initial point and head would be called the terminal point. And what we're going to see is that all of those trig identities and trig equations and trig expressions that we worked with in the previous two chapters are really going to play a big role in how we represent vectors. So maybe we'll give this vector a name. Maybe we'll call it A. And so if I draw my vector and I call it A, I'm going to put a little straight line with kind of an arrow onto it to indicate that it is a vector, not simply a line segment. And once I've got this vector, I can put it anywhere I want. So we will typically kind of think of our vectors in the coordinate plane. So we'll add the coordinate plane to describe our vectors. But our vectors can really be anywhere in the plane. So I can duplicate A and really put it anywhere that I want to. But its interpretation is typically going to be most useful to think of it at the origin because the angle for its direction will be more obvious. And then we can apply some right angle trigonometry onto it to find its magnitude. So also to start, some things that we can do with vectors. Obviously, if I want to make the vector larger or smaller, I can stretch it or compress it like we did functions. And so that is going to be what we call scalar multiplication. So if I wanted 2 times A, I would get a vector that is the length of 2 lengths of the vector itself, but in the same direction. So if this angle was in 30 degrees, say for its angle of direction, 2A would also have an angle of 30 degrees for its direction. And what we'll note here is that this is just going to be duplicating the vector twice onto itself. We can also shrink our vector. So again, by multiplying by a number smaller than 1, let's say 1/2. And what we'll end up with is a vector with half of the magnitude or half of the length. But this vector will still have the same direction. So something to note for scalar multiplication is it doesn't affect direction. So obviously something like rotation would affect the direction of a vector, but scalar multiplication does not. And then we can also think of, well, what if I multiply by a negative? So let's say I wanted negative A. Well, in this case, this negative, this reflection sort of operation we can think of, is going to take our vector, and it's still going to look exactly like it did before, but it does change the direction. So if we want to change the direction to the opposite direction, we can use this multiplication by -1 or just the negative value in general times some scalar quantity. So it could be -2, -3, etc. And so that is going to change us to moving in the opposite direction. So that's going to be a 180-degree rotation in direction. So the question might arise, well, can I multiply two vectors together? And what does that multiplication mean? So that's something that we're going to get into next time in the next set of notes, which will be on the dot product. And so that'll be for the next set of notes. So now we want to look at maybe combining two vectors with addition or subtraction. And so this is going to be pretty straightforward, which is that if we're adding two vectors, we can actually use a parallelogram as reference for this addition. So if I have two vectors in the plane, we can think of the two vectors either together, where v and u are measured from, say, the origin or from some fixed position, or I can add on one vector to the other at its head, right? So if I'm doing u plus v, that would be the same as taking u and then adding v. But something we could note here as well is that I could have also started with v and then added u. And what we end up with when we add vectors is we get this diagonal of a parallelogram. But what that's going to look like in actual calculation is simply going to be adding the components of those two vectors. So when we write the components of our two vectors, which we'll talk about on the next page a little bit, we're going to use an xy sort of representation that we normally use for coordinates. We're going to add in these little arrow brackets on the ends here to indicate that it's a vector quantity. So suppose u is the vector AB and v is the vector CD, then u plus v is going to be the sum of the corresponding components. So a plus c, comma, b plus d, which is going to be that coordinate that is the diagonal from that kind of origin location to the end of the parallelogram there. And note what we'll typically do here is add in a coordinate plane to represent our vectors. So we'll note u has coordinates AB. That's going to be the horizontal and vertical components. And then v similarly would be C and D for its horizontal and vertical components. So there's going to be a lot of useful applications of the coordinate plane when we work with vectors as well. All right, so we'll make this our first stopping point here. So when we come back in the next set of notes, we'll look at subtraction as well as kind of just getting through the algebra of working with vectors in the coordinate plane. So until I see you next time, take care.